Chem 307 experimental chemistry. I've gone through your manuals and I looked at some of them that I think likelihood that you might see something similar. We would start with the use of UV visible spectrophotometer. Okay, this is more like where this experiment started from. Your practical virtually started from. So we would want to break it down, and it's important that you know it. It's based on what is called the Beer Lambert Law. It's based on Beer Lambert's principle. That has to do with the amount of light that is being absorbed or transmitted by chemical species, and it's actually directly proportional to concentration and path length. So absorbance, right? So this basically Beer Lambert's law. It is the principle upon which UV visible spectrophotometer is based on. You should know that. All right, I think it's something you already know, but then I would critically focus on some aspects of it. You already know that according to Lambert suggested that absorbance is directly proportional to the path length, right? And usually this is a proportionality sign. So usually if you want to eliminate the proportionality sign, you introduce a constant. So that constant A, let's say is KL, all right? This is according to Lambert. Then according to Beer, he postulated that absorbance is directly proportional to concentration. Okay, and in that case, there is also a constant. Let me differentiate the constant by this prime. All right, so it's the combination of these two principles that gave birth to why we're able to use the UV spectrophotometer. So when these two are combined, it gives birth to this equation, A being directly proportional to path length and concentration. Can you see? So basically have what they have in common is concentration and path length. So, and that is why we have A absorbance being directly proportional to the concentration and the path length. So in order to eliminate this proportionality sign, we introduce a constant which is epsilon. Sorry, let me wipe this. Epsilon, concentration, and path length. So you should know this equation very well, and you should know the individual, what they stand for. This is absorbance of the species of interest, right? The absorbance value. This is a constant called the molar absorptivity. Molar absorptivity. It has a unit. You should know the unit too. All right, we make use of the molar absorptivity when the concentration you see here, concentration is usually mole per dm cube. So that's when we make use of the molar absorptivity. Then we have the path length. That's the distance traveled by the light through the cuvette and through the species of interest. Okay, light has to pass, some are absorbed, some are transmitted. You understand? So we don't want to go into that. We just want to go straight ahead to what you are supposed to at least know. All right, so with that being said, don't forget I've just mentioned the parameters for Beer Lambert law. You should know what those parameters stand for. It could be of help. And again, is in the plotting. Usually we get to plot a graph that looks just absorbance against concentration. All right, the amount of light absorbed by this chemical species, we tend to make use of it to understand or get to know their concentration, which is important. So, and this kind of curve is what we call standard curve. You could be asked, what kind of curve is this? Okay, fine. Standard curve, or you call it the calibration curve. So these are the right names. You could call it standard curve, you could call it calibration curve. So if, for example, for a particular substance, you've plotted the graph, and then you were asked to find the absorbance at certain point, and let's say you knew the absorbance. Let's say the absorbance was at 4, and you are supposed to know the concentration. You were asked to find the concentration. What you need to do is to extrapolate to the line, then downwards. Whatever this value here gives you is the concentration of the absorbing species. All right, concentration in mole per dm cube. All right, so usually the path length, the distance moves traveled by the light through the medium, is usually given. You could have the path length, which is L. You could be given, let's say, which is the typical distance. Okay, so if you're given this, and probably you're given, you know, the concentration and you know the absorbance. So that means if you have the relationship A equals to epsilon Cl, right? So if, for example, you know the absorbance, you know the concentration, all right, and you know the path length. This is in a case probably you are given something like a table that could have maybe concentration and path length. You know, path length is constant. Then probably you're given a table that looks like maybe absorbance, and you're asked to find or plot a graph of absorbance against concentration. You can do that. Or probably you're asked to find, if you look closely, this is epsilon, this mole absorptivity, right? That means we can actually also get to find the molar absorptivity. Molar absorptivity, if you make E, that's the epsilon, the symbol, the subject is going to be A over Cl, meaning that you can also calculate the molar absorptivity, right? So, and if you can do that, fine. And you can also get to determine the molar absorptivity actually from the graph. You know, if you find the slope of an absorbance concentration curve, all right, the slope is what gives you the molar absorptivity. You should also get to, you know, I'm just trying to break down the graphing. All right, so one way you can get molar absorptivity is by calculation, or you can get it from the graph by getting the slope of the. You should know how to plot your graph, know how to choose the right scale, right? I don't think we'll be going into that, how to choose the right scale, but you should know how to do that. It's something basic. Let's say we have a sample that was carried out or subjected UV spectrophotometer, and probably let's say 0.5. Let me just try to see 0.5 gram of an ink sample. I'm not saying it might be any kind of sample. I'm just trying to be representative. Okay, so if we have 0.5 gram of an ink sample that gave, or let's say that gave or yielded, okay, an absorbance, let's say of 0.4. all right, let's say the volume taken using 20 cm cube. All right, this was the sample, the volume of the sample that was used, that gave the absorbance of 0.4. This is the mass of the sample, all right, and this is the volume, all right. And then you are asked probably, or you were told that, let me put a comma, that the concentration, after you've plotted the graph, concentration, plotting the graph, I mean here, maybe you knew the concentration, all right, or the concentration was given. For example, if the concentration is given, or you calculated, or you found it, all right, and it was found that on extrapolation, I mean is when you've plotted the graph and you drew this line like this downwards to find the concentration, So on extrapolation, let's say it's on extrapolation, let's say yielded a concentration of, let's say, 1.4 mole per dm cube, right? And then you are asked to find, let's say, find the percentage of ink sample, should we say ink sample? Okay, you know, ink contains dye, right? So let's say find the percentage of the dye, all right, in the sample, you know, that gave the result. That's, let's say, that gave the above result. So basically, I'm trying to simulate something that would lead you to doing further calculation in the Lamberts law, the use of, you know, calculation, percentage, and the rest. You know, the application of, you know, the standard curve. Okay, let's say you have an ink sample, 0.5 gram, and the absorbance was run, and it gave 0.4 absorbance using this volume. And on extrapolation, like I've said, a concentration of 1.4 was achieved, and then you're asked to find the percentage of dye in the sample. Now, dye typically contains carbon, all right? So let's have in mind that dye typically contains carbon, right? It's a major element in dye is carbon, right? So now, how would you calculate the percentage of the dye, which is typically carbon, in the sample, all right, which is the ink, all right? Now, if you want to do such calculation, you would want to find first the number of moles, all right, of the dye which contains carbon, all right? And for you to find the number of moles, if you look closely, you were given volume, and you know the concentration. So you're typically going to multiply concentration by volume, meaning the concentration you are given is 1.4, right? 1.4 mole per dm cube. So volume is 20. So I won't just be multiplying by 20. I'll be dividing the 20 by 1000, because we are working in dm cube. So we are converting cm cube to dm cube. So if you do this, let me see what it's going to give me. Right. So it's going to give me 0.028. All right. So now that you've calculated the number of mole, right, now it is time to find the mass of dye. What mass of the dye? That's the carbon in the sample of ink. So for you to find the mass of dye, which is carbon, let's just say carbon, for example, you have to say moles, number of moles times molar mass. You know, number of moles equals to mass over molar mass. That's mass concentration, or mass of substance over molar mass. So if you make mass of the substance, which is carbon, typically found in dye, the subject, you're going to have moles times molar mass. So your moles is this value. So you have 0.028 multiply molar mass of carbon, 12. So if you do this, you should be having, let me multiply this here, 0.028 times 12. Okay, I'm getting 0.34. All right, 0.34. So that means this is going to be the unit mass gram. Okay, So once you've done this, remember we want to find the percentage. If you want to find the percentage, you have to relate with the initial sample weight. So we can see the mass here. So basically what we will have to do is 0.34. Let me do this over here. Percentage will be 0.34 divided by the initial sample that was given is 0.5. As you can see here, 0.5. So it's going to be 0.34 divided by 0.5. Then multiply this by 100. I don't have much space here. So if we do this, let me see what I get here. Getting 68%. You see, this is typically the application of Beer Lambert's law to concentration, to volume, and all of that in a sample. The sample must not be necessarily a dye, it can be anything. All right, so but you should know some of these things. Okay, let's look at the acid dissociation constant. So we know that the acid dissociation constant, or we call it the acidity constant. That's another name, acidity constant. So it's just a way of quantitatively measuring the strength of an acid, or acid strength in solution. So this is a way we get to know the strength of an acid in solution. So in solution, yeah. So I'm basically I want to focus more on the calculation aspect of it, graphing and the rest. And going through your manual, we had something that looked like you were given let's say serial number, say volume of A, volume of B, right? So, and you are given pH, or you expected to find the pH of different chemical species. We have something like A and B. If I'm not mistaken, ethanoic acid and sodium ethanoate. Okay, so they will serve as our A and B, and then you probably expected to say, let's say 2, here is 3, let's say here's 4, here's 5, this serial number, and usually you're mixing these two, all right, and you expected to find the ratio of the concentration. In this experiment, the concentration is measured in terms of volume, so you're basically taking the volume. So if you're doing A over B, that means you're saying 3 divided by 2, which is 1.5, like that. So then 5 divided by 4, whatever it gives you, you put it. So, and basically in the experiment, I guess you were expected to find pH, let's say 1.5, let's say 6.1. These are I'm just assuming things here. All right, so where I'm going to is in the aspect of plotting a graph. For you to find the dissociation constant of an acid, you need to plot a graph, right? So, but before then, you know, usually you get to find the log of A over B. So whatever value you get here, you find the log, you put it, it could be running in negative, all right, or positives, whichever be the case. You should know how to do these things, and you should get your calculators ready just in case. So, and if you're plotting a graph to find the dissociation constant of an acid, it's a graph of pH, usually a graph of pH against the log of whatever concentration or the chemical species you have in. Okay, so depending on the variables or whichever variables is being given. So you need to know how to plot a graph, right? So basically, while you're plotting a graph, the graph could look like this, something like this. So while you're basically plotting a graph, is for you to find the pKa, all right? Oh, sorry. Find the pKa, which can also help you in also finding the Ka, all right? You should know the difference between these two. We shouldn't be going into that now. All right, let's say for example you plotted a graph that looked like this one I've just drawn here. Let's say this is 0 and here is 0 0.1 and here is 0 0.2. You know, on this side is minus 0 0.1. So you should know how to take your scales basically, right? And then how would you get to find the pKa, right? pKa from the graph is taken as the pH value. Remember, you're plotting a graph of pH against log of the ratio divisions you made. You took the log, okay? So pH is taken from the graph. That's the pKa, I mean, it's taken from the graph as the pH value. This is pH, the vertical one, the pH value, when log, let's say A over B concentration in this experiment in form of volume is equal to 0. All right. So once you've prepared your table, you could possibly get a 0 in between. That is why the graph is always like this. Okay. So when you get a 0, so the value you get, all right, when this expression gives you a 0, tells you the pKa of the acid. So let's say you found it here. You just have to take the value here. If it's 1.5, you write 1.5 is pKa, right? And from pKa, we should be able to know how to find the Ka, all right? In your manual, an expression was given that pKa, all right, is equals to negative log of Ka, right? So that means if here is 1.5, for example, so you're going to have minus log Ka. What you basically do is to take the log of both sides to make a Ka the subject. So it's going to look like this. Ka equals to 10 raised to power 1.5. If that is the case, you know, this could be positive or negative. So whichever be the case, if it's negative, you put it, then whatever you get when you solve this, you should be able to get the Ka of the acid. So that's basically it. And you know, we got this expression from the general equation that looks like this. pH equals pKa plus log. You should see that expression from your manual. I saw that expression there. So you should know how we come about this, right? You know, the A concentration, for example, is the concentration of the conjugate base, while B is the weak acid concentration, right? So basically, if you tend to make this one the subject of the formula, you can go ahead and do that. If you want to, then just log A over B equals pH, collecting like terms, oh sorry, minus pKa. All right, so what this basically means is that if you take the exponential of both sides, you should be having something that looks like this. A over B, all right, equals to 10 raised to power pH minus pKa. Sorry, this is basically pH minus pKa. All right, 10 raised to power that. It shows that the pH of a solution can be related to the concentration of the acid. Concentration of the acid, that's the weak acid, and its conjugate base, and to dissociation constant, right? So that's basically it. You should know how to plot graph. You should know how to interpret, whatever is given. I would really get to end it here. That's the little I can do for your revision, and all the best.